Okay, this is the Functional Programming Toolkit. My name is Scott Wlaschin, that's me on Twitter, and I have a website, fsharpforfunandprofit.com, which is about F Sharp, as you can probably guess. I'm going to be using F Sharp for the code examples, but in fact, this is a concept talk. It's a big picture kind of concept talk. So these concepts should pretty much work in all modern programming languages, maybe not in COBOL, but they should certainly work in JavaScript or Python or whatever. So the first thing is, why do functional programmers use such strange words? They use words like functor, catamorphism, and applicative, and monoid, and currying, and monad, the worst word of all. And I think part of the point of this talk is to say that really, don't be like Homer and like put your hands to ears. It's not that scary. It's not really that scary, it's just that unfamiliar. And so one of the goals of this talk is to make you more familiar with some of these words. So, unfortunately, these words are not friendly words. If they were called aggregatable or chainable or mappable, like they would be in OO or something, then they might not be so scary. And you might just say, well, I don't know what they mean, but I can learn what they mean. It's not a problem. But because they're kind of mathematical sounding words, people get very scared and very put off. So please don't do that. It actually is worth learning them. And I'll tell you what's really scary is object-oriented programming. If you're a novice object-oriented programmer, you've got all these words like polymorphism and inheritance and interface and generics and covariance and solid is 5 other things, and then there's IOC and DI and MVC. So you forget, because you're experienced, probably I hope you're experienced in OO, you forget that there's all these complicated words in OO too. So functional programming isn't actually any worse than OO that way, it's just they're different words. So don't ever say that functional programming words are scary. Now, even though these have a mathematical basis, they're actually very useful tools in everyday programming. It's not just academic concepts that we're talking about here. And so this talk is really to show you some of these tools and how it can actually be used to solve real-world problems, not just kind of academic problems. So just like OO people have the OO patterns and so on, functional programmers have a standard set of tools. And I'm going to call this the functional toolkit. And just imagine just like you have a toolbox and there's a bunch of things, you have a saw and a hammer and a wrench and a screwdriver, whatever. Functional programmers, they have map, they have return, they have traverse, bind, lift, flat map, combine, whatever. There's actually about 11 tools that you need to understand. So these are tools designed for problem solving. Like I say, they're not just academic tools with no purpose. These are actually useful tools that are used every day. And they solve the kind of problems that you have as a developer. So, how do you compose things? How do you make bigger things from smaller things? How do you combine things? How do you aggregate things? How do you loop over collections and stuff? How do you work with effects? Now, I'm going to explain what I mean by effects later on, but effects is basically some extra enhanced data or something. So when you mix things up, when you mix a list and a non-list, how do you work with that? When you need to chain lists or tasks or asyncs or promises in series, how do you do that? If you want to do stuff in parallel, how do you do that? If you want to mix and match lists and tasks, something, how do you do that? So these are very common problems, and this is what the toolkit solves. So I'm going to give these things names. So the compose function, whatever it is in your language, is for composition. Fold is typically used for looping over collections. You can combine things and reduce things with functions typically called combine and reduce. Map and return are very common. Bind and flat map are very common. Apply, lift, zip, other functions. Sequence and traverse. These are all really common functions in your toolkit. And like I say, it's about 11 of them, 12 of them, whatever. And if you know how these all work, you have all the tools you need to do functional programming. So it's actually a smaller tool set than probably for OO. Now, of course, there's the jargon version of these words. This is like the friendly version. The jargon version is when you're talking about combining things and aggregating things, you use monoids. And when you're working with effects, you use things like functors, monads, and applicatives. So this is the jargon version, and I'm going to mix and match between the jargon version and the non-jargon version. So don't be put off. So in this talk, I'm not going to be talking about monoids. I'm going to talk about basically working with effects and how you work with them in parallel, how you chain them together, how you mix and match them, and so on. So that's what this talk is about. Right. Now, it's only an hour and there's a lot to cover. So this is like one of those tour buses. You go to a city and you just drive by the sites really quickly. That's what this is like. You're really not gonna get everything in a whole hour. So hopefully that will demystify and you can go away and learn it by yourself and get more into it if you want. So don't worry if you don't understand everything. Like I say, it's really just to demystify it and make sure that it stops being scary. So I'm going to talk about the core principles of functional programming. Then I'm going to talk about function transformers, which is really the main idea behind all these things. And then I'll look at some of the tools, which is map, bind, and lift. And then I'll look at a real-world example of how you combine all these tools together to actually do something useful. And it's really how you think about using these tools. It's a sort of way of approaching problems. So part one, I'm going to talk about functional programming. What are the principles of functional programming? Now, this is my take on it. Everyone has slightly different takes, and I like to put this at the beginning of my talk because I like to re-emphasize this every single time. So one of the main principles is that functions are things, right? And I like to use a little railway track analogy, like if you're playing with wooden railway sets or something. And that means that you can use them like integers and strings and dates and stuff. They're just things, so you can pass them around as parameters. And then the second really important principle is that you use composition as your fundamental tool for building things. And that is like Lego. So if you know how to use toy railways and you know how to use Lego, you know everything about functional programming. So let's look at functions as things. So I like this railway track analogy a lot. You're going to see me doing it over and over again. So imagine there's a little railway track and there's like a tunnel on the railway track. And something goes into the tunnel as one thing and it comes out as another thing. So it goes in as an apple and it comes out as a banana. So we call this as a function that turns apples into bananas. Okay, and we write it apple, arrow, banana. Now here's the thing, unlike object-oriented programming, functions are standalone things. They're not attached to a class. And that means you can use it just like an int or a string or whatever. It's just a value that you can pass around. And in particular, because they're standalone things, that means they're reusable. So the way you use functions is very different from the way you use objects because any function can typically be used anywhere in your code. So let's look at a function that has a normal input, but it spits out a function as an output, right? So you can have a function that spits out a function as an output. You can have a function as an input that returns a normal thing. You can even have a normal function, but it has a special kind of function parameter that controls how the function works inside, which in OO we call that strategy pattern. So that's all it is. That's functional programming right there. But you can really build complex systems from this kind of basics. So for example, you can have a function that returns a function that constructs another function that is another function and transform. It can get really complicated, but the principles are basically straightforward. And most of the tools in the functional toolkit are function transformers. They are functions, you feed them in a function and they spit out another function which is tweaked of the original function. It's been changed somehow. So I'm calling those function transformers. So that's functions as things. And the second thing is you use composition everywhere. And if you're familiar with Lego, you already know how to do this. So in Lego, there is actually a philosophy behind Lego, and is that all the pieces are designed to be connected. That's thing number one. And if you connect any two Lego pieces, you get another thing that is another kind of piece of Lego. You can still kind of keep going, right? And the pieces are reusable, right? So here's some Lego. Notice that every single piece of Lego has a little bump on it, or multiple bumps on it, and that's how you connect them together, right? But they're designed that way. When you make a piece of Lego, they actually think about where to put the bumps, right? They don't just design it without bumps. And because of these connection things, you can take two pieces and connect them and make another piece, and then you can take that and connect another piece, and take that and connect another piece, and take that and connect another piece, and so on. This thing that you can keep getting more and more pieces, you don't need a special adapter to add Lego to another piece of Lego, and you can keep adding and adding. You never have to run out. You never have to stop at some point because you've run out of bumps. And of course, Lego is reusable. You can make something out of Lego, and you can take it apart and put it together another way. So that's why Lego is such a fun thing to play with. And the reason why the pieces are reusable is they literally do not have strings attached. you can take, if the Lego had string attached, it would be really tangled up. They are completely independent. They have no dependencies on the outside world, and so they are completely reusable. And we do the same thing with functional programming. We try and design our functions so that they have no dependencies on the outside world, and that means they're completely reusable. So the Lego philosophy allows you to make really big things by building bigger things from smaller things, right? And I call that the power of composition. I have a whole talk about that. So how do we apply these ideas to programming? Well, let's transfer these ideas to programming. Now, in this talk, I'm talking about statically typed functional programming, but in fact, a lot of these ideas will also work for non-statically typed too. So you design functions that do one thing well, and these functions can be reused in different contexts. And you design the functions to work together. They all have bumps on them. And that means basically when you're coding, you always think that somebody could be using this function in a way that I didn't think about. So you try and design the output of the function in such a way that people can't mess it up. And then you use the types in order to make sure the bits fit together. Like with the Lego, you can't push them into the wrong slots. So doing the things that do one thing well, designing those little functions, that's the toolkit. Those 11 functions in the toolkit are very, they're tools that they do one thing really well. You don't use a hammer for hitting nails, They do one thing well, and you can reuse them for that one thing. So, composition. This is how you compose two functions. Here we have two functions. One is an apple to banana function, and another is a banana to cherry function. How do we connect them? Well, this is why I like the railway analogy, because it's really obvious how you connect them. You just stick them together. So that's before and that's after. Now, what's interesting is we now have a new function, and you cannot tell it's built from smaller pieces. The fact that it's made from smaller parts, you can't tell. All you can see is the input and the output. For example, where did the banana go? Right? The smaller functions cared about bananas. This function doesn't care about bananas. And so if I'm using this function, I don't need to know about bananas. So this kind of composition thing, you might think, well, yeah, but can how far can you go with this? So you can start with low-level functions like uppercasing a string. That's a really simple function, right? You give it a string and you get a string back. But you can take these low-level operations and build them into like a service that does something like a address validation service that you feed in some sort of address and it spits out a result. And a service is a bit of a strange word, so anyone under 30, a service is just like a microservice. Yeah, you have to be over 30 to get that joke. All right. So we take these services and we combine them into a use case or a scenario or a story or a workflow, whatever you want to call it. They do various things. They can work together to make something happen. And then finally, you take all these scenarios or use cases, whatever, and you build a web application. Now, a web application is actually a function. It takes in an HTTP request as input, and it spits out an HTTP response as output. So you can actually think of the entire web application as a function. And inside there, you have a controller or a dispatcher or a router, or whatever you want to call it, that decides based on the input which one of these things to call. So that's a complete application built from functions. And so you can say that composition is sort of fractal. It works. You use the same techniques at the low level as you do at the high level. That you don't have to switch between different techniques. Just like with Lego, you use the same techniques as the Lego when you're putting two pieces together as when you bring big things together. So if you look inside a web application, this is what it looks like. There's these functions all chained together. But notice the arrows go in one direction. So unlike OO, where you can have kind of dependencies and all sorts of things, in functional programming, you tend to have this linear pipeline thing where things tend to go in one direction. So that's the power of composition for functions. As I said, I've got a whole talk on this. If you go to my website or just Google power of composition, you'll find it. Right, so let's look at how this works in F#. So I'm going to show you some F# code now. Here is a very simple function F#, adding 1. Here's another simple function which doubles it. And in F# we use the let keyword to define things. In C# you use var, or in other languages it's def, in other languages, whatever. So that defines a function. And you can also define functions using lambdas, using the fun keyword, because fun is a keyword in F#. That's why F# is so great. So this is how you do a lambda in F#. Right, so you can. I'll switch between defining functions both ways. Right, so let's compose some functions. Now, you say, well, let's say I want to add 1, and then I want to double it, and then I want to square it. Now, in a traditional programming language, you do this by using lots and lots of parentheses. And this kind of nested thing can get kind of ugly sometimes. I don't know. So you have to kind of work from the inside out. Now, a model that I think is much nicer is this pipeline model, where you start with a number and you feed it into add 1, and you take the output of that and you feed it into double, and you take the output of that and you feed it into square, and so on and so forth. Now, anyone who's done any kind of Unix command line, programming, this is, you have the pipe on the command line. It's exactly the same technique. And I think this is actually a much easier model to understand, and the functional programmers tend to use this a lot more. So in F#, the way you do this is you have a special pipe symbol, which is a vertical bar with an angle bracket. And I take 5 and I feed it into add 1. I take the output of add 1, I feed it into double. I take the output of double and I feed it into square. And you just pipe the stuff all the way along. So that's how, when you look at F# code, you'll see a lot of code that looks just like this. Right, so that's composition. Of course, it makes it sound too easy, right? In real world, it's never that easy. There's always complications. So let's look at some of the complications. What happens if the inputs and the outputs don't match up properly? So if the output is a banana and the input of the next one is a banana, everything's good. We're very happy. But if the input of the next one is a cherry, the banana and the cherry don't match, and you can't compose them together. So one fix for that, that doesn't work. One fix is to insert some sort of conversion function into the pipeline. So we have a little apple to cherry converter, and we just stick it in the pipeline, and then everything works. Let me show you some real code here, because it's a very contrived example. But let's say that we take the output of add 1, and we want to feed it into string length. Now, string length doesn't take ints, it takes strings. So you're going to get an error when you try and do that. So the solution is to stick a new function into this pipeline that turns ints into strings. And that fixes that problem. So that's pretty easy. But that tends to be really not the most important problem that you run into. So you can fix things that way. More likely is you have a situation where the types are sort of the right type, but they're wrapped in something and they don't match. So you might return an optional value, an optional banana, and you need to feed it into something that has a banana, and the optional bananas and bananas don't match up properly. Or you have something, a banana, and you need to have a list of bananas, and you can't turn a banana into a list of bananas. So they kind of match up, sort of, but they still don't really connect together properly. And this is really what we're going to solve with the functional toolkit. Right. The spoiler to this, by the way, is monads. Right. Right, so part 2, let's talk about function transformers. So we've got the basic problem of composition. How do we compose things that don't fit properly? And really, this is what we'll spend the rest of the talk talking about. So we're going to use railway analogy again. Railways. What do railways have to do with programming? I keep talking about it. So here's a real-world scenario. Let's say that I have a web API, a web service, and I want to update my name and email address. So I'm going to receive a request, and the request contains a name and an email, say. And I'm going to validate the request. Is the name not blank? Is the email a valid email, and so on? Maybe I'm going to lowercase the email, maybe trim stuff from the string, and then I'm going to update the database. Okay, pretty simple, straightforward kind of thing to do. Now, let's look at some code. So this is some C# code. And we do the thing, we take the request, and then we validate it, and then we lowercase the email, and then we update the database, and then we return okay, whatever it is. That's great, it's really nice. It's just a few lines of code, everything works great. The only problem is we don't have any error handling. So this is actually not production quality code. Let's add the error handling, okay? Now, as soon as we add error handling, we have to say, well, what happens if the validation doesn't work? What happens if you can't find the customer record in the database? What happens if the database throws an exception? All sorts of things can go wrong. And your nice, clean code, your couple of lines of code, ends up being really ugly and really complicated. And that's a shame, because it was, if we didn't have to do error handling, it would be wonderful. Now let's look at the functional equivalent. So what we're going to try and do is preserve the simplicity. The original version looked really nice. It was very simple, but it didn't have any error handling. Now the production quality version is much more ready for production, but it looks horrible. So can we get the best of both worlds? Can it still look simple, but still do the error handling? So we're going to use this type that functional programmers use a lot, which is result type. And the result type is basically a choice. When you do something like this, you validate something. you can either success or failure. It's like it is valid or it's not valid. And we represent this with a choice type. And this is how you write it in F#. It's basically a choice between two things. You can think of this as an enum. You can think of this as a class with two subclasses. It doesn't really matter how you think of it, but it's basically you've got a choice between two things. And we, in functional programmers, call these sum types. Now, let's actually see how this works. So if we're going to validate an input. If the name is blank, that's bad. So we're going to say that's an error type. We're going to use the error choice. If the email is blank, that's also bad. We're going to return an error. But if those are both fine, then the whole thing is good. So we're going to say that, okay, we're going to be on the happy path. Right. Now, what's interesting from the railway point of view, this looks awfully like a switch function or a points function. You have one input and you have two outputs. So this is the metaphor I'm going to use. And you often run into the situation where you have like a validation function and it does something else, and then there's another function, and there's like one input, but every possible thing could have an error. Everything could possibly fail. And now the question is, how do you connect these kinds of functions together? Now, if you're a railway expert, you'll know how to do this, right? Because you just do that. So that's before they're connected, and that's after they're connected. So it's actually really obvious how to connect them, kind of, if you think about it, but now the question is, how do you actually implement this part? So I call this the two-track model of error handling, otherwise known as railway-oriented programming. And again, I have a talk about this if you're interested. So if we go back to the original code and we update the customer, we know this is the functional version now. We've got the F# code with the piping and everything. We take the request, we pipe it into validate, we pipe it into lowercase, we pipe it into update, and so on and so forth. So that's the one-track version without any error handling, just like the C# code. Now let's look at the same version with the error handling. Okay, so that's before. Now with the error handling, what does it look like? It looks like this. You take the request, you validate it, you feed it into lowercase email, you update the database, and so on. And you're thinking, well, that looks just the same. How can it be any different? Where's the error handling? And the answer is because this is actually a two-track model. So the error handling is built into the way the two-track system works. So you get to preserve the elegance of the original version, but you still get all the benefits of the nice error handling. Right. So let's actually look at the real code for implementing this stuff. So this is the function we have. We've got input, we've got success and failure. We want to connect these functions together, and we want to say, well, if it succeeds, we want to do the next thing. If it fails, we want to bypass. We want to get onto the error track, and we want to just stay on the error track. If we can't validate the input, we're never going to update the database. So we want to get to this point. We want to connect them together. So how do we compose these things? Well, if we had one-track functions, we could compose them, because we just connect the input to the output. And if we had two-track functions, we could also compose them, because we connect the success track to the other success track and the failure track to the failure track. That would work fine too. But we don't have that. We have this. We have one input and two outputs. And this doesn't work. So this is our problem. How do we combine these mismatched functions? And the answer is bind. This is a word you're going to hear a lot. Functional programmers love the word bind. They get very excited by the word bind. We're going to bind all the things. So here is our function. And as we said, it's not suitable for composition. However, if we had a two-track version of that function with two inputs, that would be perfect. That would be just what we need. Now, here's the problem. How do we go from the top one, which doesn't work, to the bottom one that does work? Okay, so what we're going to do is create a little adapter block. And I think even the wooden railways have something like this, right? You have a little square thing and you slot your thing into it. So there's a two-track thing and it's got a slot for the points or the switch. And we put this in the slot, and what comes out is one of those. So this is an adapter block that turns these switch or points functions into these two-track functions. This is exactly what we want to solve our problem. This is a function transformer. It takes a function as input and spits out another function as output. So the implementation is actually really easy. I'm going to say bind. It's got two parameters. We pass in a two-track input. We're going to compare, is it the OK case or the error case? If it's the OK case, then we're going to call the next function. If it's the error case, we're going to skip. We're just going to stay on the red track and not do anything. So that's the complete implementation. So the implementation is literally 3 lines of code. We're going to find all today that I spend more time explaining something than writing it. Once you understand how these things, literally the implementation is trivial, but the understanding is harder. So once we have this bind function, we can take our points functions like this, and we can turn them into bind, and we can connect them together. So this thing of using function transformer to convert things from one thing is just like the most important concept to understand. And let's look at another example. Let's look at how you do validation. So let's say that we want to validate the input again, and how do we do that? Now before I put it in one giant function, but probably you want to break it up into pieces. So I might want to validate the name is not blank, and maybe I want to make sure the name is less than 50 characters because I'm putting it in a database. And maybe I need to check the email's not blank. So writing smaller functions is nicer because each little tiny function does one little thing, and they're reusable. I could reuse the email one in another context, for example. So we have all these. Each of these little functions is one of these 2-track output functions. And again, how do we combine them? Well, the first function we're going to leave alone. The second function we want to compose with, and the third function we compose. Now, in order to actually compose them, we'll have to convert the other two into these 2-track things. So we use bind. So the first one we leave alone. We do bind on the second one. We do bind on the third one. And once we've done that, we can connect them together. So let's actually look at the code. We take the first one and we pipe the output into the second one, and we pipe the output into the third one, assuming they've used bind on them. So now that solves our value. We've got these individual pieces and we've composed them into a chain. And what we can do is we can give that whole thing a name. We can say, to validate the input, here's the 3 little functions we're going to use. We're going to chain them together like that. And we're going to give it a name. We'll call it validate the input, just like we did before. And what's cool about this is if we treat it as a black box, we now have another function with 1 input and 2 outputs. So this bigger function looks just like the smaller functions. Just like the Lego, we can keep going and going. We can build a bigger. We can actually connect this to the other things and build a bigger function out of it. So this is how you can build. You can see how you can build bigger things from smaller things nicely. So we just keep going and going, and we're done. Now, one thing to point out is that the shapes and the types are a kind of different concepts. When we're talking about composing the 2 tracks, we're talking about the shape of the track, right? Now, the type of the data that goes through can change as it goes through. So we could start off with an apple, and it can turn into a banana, and it can turn into a cherry, whatever. So the type can change as long as the shapes match up. So transforming the data is fine. They don't have to be. So here's an example where the types match up. The bananas are the same, and the cherries are the same, and the shapes are the same. So that's good. Now sometimes the shapes do match up. They're both 2-track, but the types don't match up. So you have a banana here and a cherry here. They don't match up. So you're going to have to use the converter thing, like I said. You have to turn bananas into cherries in order to make it work. Right, so that's that. Now, one thing we've talked about is these 1 input and 2 outputs, but sometimes you have functions with 1 input and 1 output. So for example, if we're going to lowercase an email, it can't go wrong. There's no error. It's never going to break. So really it's just a 1-track function, 1 input, 1 output. So how does that fit into the model? The way we're doing it right now is it doesn't. So what we need to do is the same thing as we did before, which is using a function transformer to convert that into a 2-track thing. And we call this map. And map works very much like bind. There's a slot. You feed in this 1-track function, and it spits out a 2-track function. And the implementation for map is really, really easy too. We just say, is the input good or bad? If it's good input, we call that single-track function, and we take the output of that and we turn it back into a success case. And if the input is bad, we just skip the whole thing. So again, it's like a 3-line implementation. So now, once we've got this map function, we can fit that lowercase email into our pipeline just by using map on it. So this is the principle we're doing here. We're converting everything into a standard 2-track. Everything is converted into the same shape, as it were. So we had a single track function, we converted it into a two-track function. We have one of these points or switch functions, and we turned it into a two-track function. And we'll find if we have any other kind of weird functions, we'll turn them into two-track functions, and we just make them all into the same kind of thing. Once they're all the same kind of thing, we can connect them together. So these map and bind are two function transformers. These are the first two, and actually probably the most important function transformers that you use in functional programming. So here's what we had before, and these things were not composable. They weren't able to be connected. But after we use these function transformers, they are able to be connected. We've turned everything into two tracks, and we've solved our problem. So there we go. That's a really nice way of doing things. So that's what function transformers are for turning the different shape functions into the same shape function. And this is really the setup for the whole functional toolkit. So before I go into the functional toolkit, I need to talk about what I mean by effects. So what is an effect? So an effect is really just a kind of generic type. Like, for example, lists is a generic list is a kind of effect. It can be a type with extra data, like option or result. It can be a type that interacts with the outside world, because functional programmers hate to have random stuff going on. It's like you want to make sure you really control how you interact with the outside world. So asynchronous stuff or tasks or dealing with random numbers or whatever, you want to make sure that's a special type. Functional programmers also use things like state and parsers, special types to represent things going on there. It doesn't really matter what it is. It could be all sorts of stuff. And it really doesn't matter what we're really going to focus on and what is common. What are the patterns which are common behind all of these things? So the implementation might be slightly different, but there's a commonality. There's certain patterns which work for all of them. So I'm going to focus on three types of this talk, which is list, option, and async. And async is the F# version of task, or promise, or future, whatever you want to call it. Right. So normal world and effects world. What do I mean by that? So in normal world, you have things like strings, and you have integers, and you have booleans, and you also have functions, and you have a function that turns an int into string, and you have a function that turns an int into boolean, and so on. So you have this kind of world of all these things. These are the things you're used to. Now, in option world, it's like a parallel universe. So everything in the normal world has a kind of mirror image in option world. So every time there's a string in normal world, there's an option of string. Every time there's an int in normal world, there's an option of int, and there's an option of bool. And just like there are functions in the normal world, there are functions in the option world, except the functions always work on options. So, instead of having int to string function, you have something that turns an optional int into an optional string, or an optional int into an optional bool. So this kind of option world is something we're going to be coming back to. Same way, there's a list world. And in list world, everything is a list. So you have a list of strings, and you have a list of ints, and you have a list of bools. And all the functions are list functions. They turn lists of int into lists of strings, and lists of ints into list of bools. Right? You can see where I'm going with this. You do the same thing with async world. Async of string, async of int, async of bool, or task of string, or task of bool, whatever you want to call it. Again, all the functions live in async worlds. So think about these worlds is going to be quite a useful technique in terms of understanding how to compose things. And you can see there's just a generic pattern here. It's like a generic effect. Whatever the effect is, there's an effects world where there's the effect of the string and the effect of the int and the effect of the bool. And all the functions are effect functions. Right? So if you can understand that, then you can understand what I'm going to be talking about next. Now, these effects is like a functional programming jargon. People call them effects. Some people call them enhanced, because it's like enhanced values. Data is like a value with extra data, like a result or an option. Sometimes I call them elevated worlds, because we often talk about lifting things from the normal world into this other world. So it's like lifting things up into a higher world or an elevated world. So I'm going to use E. Everything's an E world. Right, so here's the challenge. How do we actually work with these things? I'll give you a real-world example. So let's say I need to download a URL, and it's going to be some JSON that comes out. Okay, so I've got JSON, and now I need to convert that JSON into, for example, a customer DTO. So, because in my domain, and then that DTO needs to be converted into a valid customer. So I'm going to do some validation on it, make sure it's good, and then I'm going to store that customer in a database. Okay, so this is a kind of example scenario. If we look at the things of how it works, we download the JSON file, we start off in the normal world, but the download, it might be asynchronous, and it might or might not work. So it's an async containing a result. So we're traveling between another world. If I'm trying to decode the JSON into one of my objects, that might or might not work because I might have got the types wrong. So the JSON is in the normal thing, it's like a string, but when I decode it, I might get an error result. It might not work. So I'm now moving into another world. When I do some validation, I start with a normal DTO and I validate each field, but the validation may be errored, right? Each piece of validation may be an error, so I have a result from that. To construct a valid customer from, if the name and the email is valid and I want to construct a customer from that, that's fine. That's all normal world stuff. So there's nothing special there. And then finally, when I want to store the customer in the database, I start with a customer, and again, it may be asynchronous and it may not work, so it's an async which contains a result. So here's the problem. How do we compose these things together? That's the problem. They're all kind of going in different directions and stuff. So none of the worlds match up. This is where the functional toolkit comes in. So let's start with options. Here's our normal world, and here's the world of options. Now, when you're working with options, you often do this thing where you have some sort of function that returns an optional value or a nullable value. If you replace option with nullable, if your language doesn't have options, just replace everything I say with nullable. So you go to this world, and then you need to do something with it, so you kind of come back down to the normal world to do something. You go back up to the option world, you go down, you go back up, you go down. This is a really bad way of doing things. So in functional programming, this is like sort of an anti-pattern. What you really want to do is when you go to the option world, you want to go up there and you want to stay up there as long as possible. Now you might have to come down at the very end, just to return a string in your HTTP or whatever, but you try and stay up in this world as long as possible. And that's the right way of doing it. So here's my add1 function. This is a normal world function. Now, if I try and use it on an optional value, I get an error because add1 doesn't work with options. It only works with normal things, right? So let's say, well, I'm going to write a special function called add1 to an option. And if the option is valid, if it's something, I'm going to call add1 on it. And then I'm going to take that value and wrap it back up in an option. And if it's not valid, I'm going to return nothing. Right, now this is the same thing I'm talking about. You're unwrapping it, you're doing the thing, and you're wrapping it back up again. This is like not how to do it. Go down, don't come down and do something and go back up again. Right. So if you catch yourself doing this, try and think about doing it another way. So what is the other way? How do you use this add1 function and stay up in option worlds? Add1 isn't an option function. So what we want to do is this is our first tool, which is the map function. It moves things between worlds. So here's our option, our add1 to option. This is a really explicit function that only works in this one particular case. Let's make it generic, right? Let's make it a generic function. So what I'm going to do is pass in a parameter. Like, what is the thing that I want to do? Well, I don't care. It could be anything. So I'm going to pass that thing in as a function, and I'm going to call it f because I have no idea what the function is. It could be anything. Functional programmers tend to use these very short letters sometimes because what else can you call it? So I'm going to run that function on whatever the value is and make something. Otherwise, it's nothing. So that's my parameterized version of this function. Well, that's good. That's better. But I can go further. What I can do is have a lambda version. So I'm actually going to rewrite this so it returns, the whole thing returns a lambda, it returns a function. And the input to this lambda is an option. And the output of this lambda is another option. So this whole thing, this lambda, is an option to option function. And the input, the parameter I've given it, which is in normal world, is a normal world function. So what we've got here is a function that turns normal world functions into option world functions. And if you look at it on the picture like this, it's like, here's my normal function, and I use this option map, turns it into an option world function. So that's what map is. Map is a function transformer that turns normal world functions into option world functions. So when I have this map function, I can then work on anything. So rather than having to write a special thing for add1, I can say option map of add1. And now the add1 has been moved into option world, and I can use it with options without any problem. Let's do the same thing for lists. Here's adding 1 to each item in a list. Okay, so for each item in the list, I add 1 to it, and I put it back in a new list, and I return the new list. Again, this is super, super specific for add 1. It's like I would never write a function like this, because I'm unwrapping it and wrapping it, applying it and wrapping it up again, doing exactly what I said you shouldn't do. You don't want to come down, do the thing, go back. So this is the same pattern. So even when we're talking about lists instead of options, it's the same kind of pattern. So even though working with lists is different from working with options, we're making the same kind of mistake. So again, let's make it generic. We're going to pass in a parameter. What do we want to do with each item in the list? We'll pass in a function f. And for each item in the list, we'll call that function f to get a new item. So now we've parameterized it. And then what we'll do is we'll lambdarize it as well. So we've now got a lambda which takes a list as input and it spits a list as output. And again, our little parameter is a normal function. So what we've done again is we've created a function that takes normal world functions and puts them into list world functions. So that's great. And now we can use it just like we did before. We can say add 1, we turn it into a list and use it for that. And people say, why is this any better than writing your own loops? It's because it's a pattern. Once you recognize this pattern, you know a bunch of stuff about it. I know, for example, I know that map can never change the length of a list. It's always going to be the same number of items. So I can just tell straight away. If I was doing a for loop or something, I would never really be 100% sure. Right, and you can do the same thing for async. You can have async map that turns normal functions into async world. So most generic functions, most generic types like list and map option, they have a map function, use it, and if you write your own generic type, write a map function for people to use. Now in FP terminology, this is called a functor. So a functor is some sort of effect type, like option or list or async, plus a map function, which is called map, or it can be called select, or it can be called lift. There's lots of different names for this thing. And it has to have a sensible implementation known as the functor laws. But basically, it's just to make sure you have a sensible implementation. Right, what about tool number 2, which is moving values between worlds? This is really easy. We have a value in normal world, and we want to move it up to the world of options. And that's normally called return. Like here's an example, it's different for each type of thing. So to make an option, you just say it's something. That's really easy. So normal world value and an option world value. And for making a list, you can take a single item and make it into a list. And list return or list singleton, whatever you want to call it. Again, to make a single item list is really easy. So there's nothing special about this type of function. It's useful in combination with other functions. Right, what about bind? That's a familiar word. So what's a world-crossing function? I'm going to be talking about world-crossing functions. So here is a function. You give me a maximum integer, and I give you a list of integers up to that maximum value. So this is a function that takes an integer and returns a list of integers. So we start, the input is a list, is a normal value, and the output is in list world. Okay, so this is a world-crossing function. You start down at the bottom, and you end up higher up. What about getting a customer from a database? You give me a customer ID, and I'm going to try and get the customer from a database. So if the customer is found, I'm not actually going to show the database code, obviously. Somehow you do the database query. If the customer is found, you're going to say, yeah, here's some customer data. I'm going to give it to you. If the customer isn't found, I've got nothing to give you, so I'm going to return nothing. So again, this is a function that crosses worlds. You give me a customer ID, and I might or might not give you back customer data. It's an optional. I give you back an optional customer. So we start off with a value in normal world, and we end up with a value in option world. So here we are, customer ID down here, option, customer data up here. These world-crossing functions are really common. So how do we chain these things together? So let's say we have options. We're in option world. We do something, and it returns an option, and we want to do something else. Well, if the option is something, then we can do the next thing. And if that is something, we can do the next thing. And if that is something, we can do the next thing. And so on. And if any of them are nothing, then we have to kind of skip, right? So this pattern is very common when you have these world-crossing functions. You have these nested checks. You keep nesting and nesting and nesting and nesting, and people call this the pyramid of doom because it looks really horrible. Now, you see this all over the world. I mean, you see this with tasks. So that, it's not just options. Tasks are the same thing. You run a task, and when the task is finished, you do the next task. And when the task is finished, you do the next task. And when the task is finished, you do the next task, and so on. Exactly the same kind of thing. You get this nested pyramid, this nested indent, and nested callbacks, and this pyramid. So anytime you have these world crossing functions, you're going to run into this pattern. Okay. So how do we solve this pattern? How do we fix this problem? Let's look at the option one, and notice there's a pattern that we can exploit. If it's something, do something, otherwise do nothing. If it's something, do something, otherwise do nothing. If it's something, do something, otherwise do nothing. That's the pattern we can exploit. So let's make a little helper function for that. We're going to call it, if it's something, then do something, otherwise do nothing. Right? That's the pattern. How do we make a helper function? Well, we don't exactly know what you want to do with it, so we're going to parameterize it with a function parameter. So here's the actual helper function. If something do, I'm going to call it. If the option is something, do it. What is it we're going to do? We don't know. Otherwise, return nothing. So whatever it is we're going to do, we don't know what it is, so we're going to pass it in as a function parameter. So this if some do is a really useful little helper function. And if we go back to our original example, we can say, well, do something. If it's something, do the next thing. If it's something, do the next thing. If it's something, do the next thing. So we've taken our kind of pyramid shape and turned it into a nice, flat, linear up and down shape, much easier to read. And let's revisit that railway analogy because it's very similar. Instead of having success and failure, we have something or nothing for options. And we've already seen this. If it's something, do the next thing. If it's nothing, bypass it. So we're going to follow exactly the same thing we did before. We want to chain these together, and we're going to use bind again. And we're going to do this thing where we have these functions that don't fit, and we want to turn them into functions that do fit. And we're going to write a bind function, which is a transformer function. And this time, the code is slightly different because we're talking about options rather than results, but the idea is exactly the same. So it's another function transformer. So in this case, to bind for options, we say, if the option is something, do the next thing. And if the option is nothing, keep going on the error path. Now, it turns out that's exactly the function we just wrote. The if something do function is exactly the same implementation. So this, option example that we wrote with the nested thing, which is ugly and horrible, we use this option bind function. Like I say, it's exactly the same as the if something do function, exactly the same implementation, right? And it's parameterized exactly the same way. And we can then turn our original ugly code into something nice and clean. No pyramids anywhere. And let's do the same thing for tasks. Let's get rid of the task pyramid. Here's how you chain two tasks together. If the task completes, or when the task completes, you do the next thing. Otherwise, if the task doesn't complete, you bypass it, right? So that's the when finished do. So let's do the same thing. Here's the untidy version with the nesting and so on, which is really ugly. So we're going to write a helper function called when finished do, otherwise known as bind, right? So when the thing is finished, we're going to do something, whatever the next thing is, but we don't know what it is, so we'll just pass in a function parameter for that. There's the function parameter we're passing in. And once we have this task finish do or task bind, we can make our pyramid logic much more simple with a straight linear line. So there you go. So bind is like one of the most important functions one of the most important concepts in functional programming because it makes world crossing functions composable. This is the original version of our function. It's a world crossing function. It starts in normal world and ends up in an effects world, whether it was an option or a list or a result or an async or whatever it was. After we do bind, we have a horizontal function. So the whole function lives in the effects world. So after we did bind, we had the option input, option output, or we had the list input, list output, or the async input, or the task input, task output, whatever. And if you go back to the railway model, it's like this is the world crossing function we had, and after we did bind, we had this nice two-track model. So you can see this is really, really powerful. And you often have this situation where you have a bunch of world crossing functions or diagonal functions, and you need to chain them together. And so what bind does is it allows them to be composed, because the diagonal functions as they stand cannot be composed. But if you do bind and you make it into a horizontal function, and you bind the next one, and you make it into a horizontal function, and you bind the next one, and you make it a horizontal function. You now have a bunch of horizontal functions, and you can glue them all together. Right? So the whole point is how can we make our functions composable? That's what bind's all about. So in FP terminology, that's what a monad is. So I've been talking about monads this whole time. Monad is an effect type plus something return plus a bind function. Basically, it's a type plus a bind function, plus some rules about how to implement it. Now, the bind function is all sorts of different names. In other languages, it's called flat map. It's sometimes called when, then do, or when do. In C#, it's called select many, if you know link. And it has to have a sensible implementation. But that's all a monad is really just a type and an associated bind operation. So use a monad if you want to chain effects generating functions in series. Right, we'll quickly talk about applicatives for doing parallel stuff. If you want to combine effects in parallel, sometimes you want to have both things. Like if you combine two options, you want to get an option that contains the pair. Like if you have some 42 and some hello, you want to have 42 and hello. But if one of them is missing, the overall thing is missing. Similarly, if you have two lists and you want to combine them, we want to get a list of pairs or something. Like here's a list of all the pairs. Or you might want to have a list of pairs that way, either a cross product or a kind of a zip list. So this is a general concept in functional programming called an applicative functor. It's the same kind of thing. It's like a monad, like a functor. It's a way of combining things in the effects world, and you preserve them. You combine them together in parallel. So let's look at an example. Yeah, there's the applicative functor. All this stuff. You don't really have to worry about the jargon, really. The jargon, I'm going to throw this out here, but don't worry about the jargon. Sometimes you see the word lift. I'm actually going to use the word lift. And sometimes you see the word apply. These are all different variants of this kind of concept. Sometimes you see angle brackets with a star in the middle. That's the Haskell version of this. Right, so why is this useful? Because you want to do things in parallel. Here's our customer, and we've got our validation logic, right? The problem with chaining them in series is that as soon as the first one fails, the rest of them fail. And we never get a list of errors, we just get the first error. So it'd be quite nice, rather than chaining them in series, where we only get one error at a time, is to get all the errors at once, all the validation errors at once. And in order to do that, we have to run them in parallel, like this. So each field gets validated separately, and then we combine them in parallel. And that's exactly what the applicative thing does. We get all the errors at once. So, just like we had before, we've got all these independent results from the validation, and we want to combine them. Now in normal world, we have a way of combining them. We just call a constructor, or a function that makes these things. So that's not a problem. We know how to combine them in normal world, but we don't know how to combine them in result worlds. And what we want to do is combine them in the result world and have the output also be in result world. So we have all these errors, and we combine them to make a customer. And if any of them are not valid, we get an error on that side too. So that's what applicatives are for. You're combining things in result world to make a new result, or combining things in list world to make a new list, or combining things in async world to make a new async, whatever. And these functions are normally called lift. Like A for applicative, lift A2 is a 2-parameter lift A3 is a 3-parameter lift. So just like we had list map, which would have a 1-parameter function lifted up, lift 2 will lift up a 2-parameter function, so this one has the 2 parameters. Lift 3 will lift up a 3-parameter function, and so on. So if you see lift, is doing the same thing as map. It's moving it from one world to another world. So if you look at the code, to convert our DTO into a customer, we validate the name. It could be a valid name, or it could be an error. We validate email. It could be a valid name or an error. A valid email or an error. We validate the birthday. It could be valid or an error. And now we want to try and make a customer out of these things. And so we use our make customer function, and we lift it into result world. And once we lift it into result world, we can pass in those 3 parameters, and we get back a result containing a customer. So that's the magic. I'm not going to explain how it works, but it is kind of magic. And we get a nice list of errors rather than a single error back. So again, don't worry about applicatives working too much. Just be aware that if you want to chain things in parallel, use an applicative. If you want to chain things in series, use a monad. All right, so let's look at the tools that we've been talking about. We've talked about map, which lifts things into effects world. Return lifts individual items, individual values like strings and ints into effects world. Bind for diagonal functions, world crossing functions. Apply or lift for combining things in parallel. Right, so let's use all the tools together. Let's actually solve that real world problem that I talked about. So we had downloading a URL, downloading the JSON, converting the DTO, etc. So, downloading the JSON file, we started with the URL and we end up here. Decoding the JSON, we started in the normal world and we ended in results. Validating the fields, we end up in results. Constructing the customer was all normal stuff, and then storing the customer in the database was from normal world to async result world. Right. So let's look at, we can use the tools to compose them. Before we didn't know how to do it, now we do know how to do it. So let's start with the validation. We've got these three results, and we want to make a customer out of them, and we saw how to do that using the applicative, using lift3. So that's good, that's one thing. So now what we do is we have a normal DTO in normal world, and we have a customer in results world. So that's that particular problem solved. So there's our DTO to customer. That's a diagonal world crossing function. We also have the JSON to the DTO. That's also a diagonal function because the DTO, the JSON might not work. It might be invalid. So we have these two diagonal functions, and we want to connect them together. We want to take the output of the JSON, which is the DTO, and we want to feed that into the next one, right? And as they stand, they can't be connected. But if we use bind, that will solve a problem. We're going to use bind and make them both horizontal, like that. Now they're both horizontal. We can connect them all together to make a big function. So now we have a big function that starts off with JSON and ends up with a customer. So the DTO is now hidden. The banana has now gone away. All right, so there's our new function. So we're building bigger functions and smaller functions. Now we're going to reuse this function in the overall bigger picture. Right, so this is what the code looks like. Again, the code is really simple. We do a bind and another bind. So literally 3 lines of code. And again, it takes much more time to explain it than to actually write it. Right, so now we have this. Now, our final thing is living up in async result world. And this is not there. This is in result world, but it's not in async result world. So we need to move it up another level. We need to move it one stage higher. How do we do that? How do we move a function from one world to another world? We use map. So we're going to use map to lift it up to the async world now. So our original function, which was kind of all these diagonal functions that didn't fit together, we've flattened them out horizontally and we've lifted them up. So now we have a final function which works up in the async world, and it's horizontal. It's going to be easy to compose. Right, now what about storing the customer in the database? That was also another diagonal function. And again, it's not composable as it stands. But again, we can use bind. We're going to take this thing, we're going to turn it horizontal, like that. And now we have a horizontal function that lives entirely in async world. So now if you look at all the different steps we have, the original step was downloading the URL, and that made an async result which contains some JSON. And now we have the JSON to customer function, which we built from the various pieces, and that now lives in async result world because we started off down in results, we did the map to lift it up. And the other function, which was storing a customer into a database, again, that was originally a diagonal function, and we made it horizontal, so it's now a purely async world function. And these are all async world functions, and they can all be composed together really nicely now. So we start here, we go up, we compose, and we can connect these together and make it into one giant function. So this is how you use the tools to do real stuff. And again, it's more complicated to explain. If we actually look at the code, there's the code we had before, and this is the actual main function that downloads and stores a customer. You start with a URL, you download it, you convert it to a JSON. You do the JSON to customer conversion, and you have to do it in async worlds. And then finally, you store the customer in the database, and that has to use bind. So it's 6 lines of code, or 8 lines of code. These patterns are very unfamiliar initially, but once you see these patterns, you'll be able to look at this code and know exactly what it does. Right, so much more time to explain than to write it. But you can get, they're common patterns, once you know what they are, it's easy to use. Right, so final thing is all this bind stuff can get really ugly. And so a lot of functional programming languages actually have support for monads built in. So for example, F# has something called computation expressions, Haskell has do notation, Scala has for comprehensions, C# has select many. So you can actually overload select many to do a lot of this stuff for you. So that's kind of cool. Right, so finally, just want to remember that functional programming jargon is actually not that scary. Hopefully the concepts make sense, even if the words are a bit scary. Hopefully you can see why monads are such a big deal, and everyone talks about monads all the time. If you think about bind instead of monads, you can see why that's valuable. This is a very generic toolkit. All this bind and map and stuff, this is a concept that works for any effects world. So not just for options, not just for results, not just for async, anything. And so as a functional programmer, you basically use these kinds of functions over and over for everything you do. And now when you see, if you look at functional code and you see map and lift and bind, you'll know what people are talking about. Like I say, don't expect to understand everything straight away. So I'm going to post these slides and videos on my website at some point. If you're interested in some of the stuff I've talked about, I have a related talk, which is functional design patterns. I have another one called the power of composition. I have another one called domain modeling being functional. And I have a whole book about domain modeling and functional. So if you're interested in that, let me know. I think it's actually for sale at the bookstore here. Contact me on Twitter, and thanks very much.